Oh,
Hello.
Hello.
hey, Burden. Hey, Jeremy. Question?
Yeah, sure. Hey, I tried to register for the 475 Tech 3, but it still isn't showing on my SIUC net.
Oh, I was told by Dr. Talapatra that it is there. Do you think you can write a quick
Yeah.
a one-line? Yeah, that might help.
I'll send one to him and I'll CC you in it. But I was just gonna let you know quickly before.
Yeah, thanks. Yeah, I will also let him know. Yeah.
Okay.
It might not show my name on it. I mean, does it show the 575 at all?
No, the only section it shows 475, but the only section it shows was for 799. It doesn't show an instructor, but it's a 3-credit 799 section.
It's supposed to be 706.
Yeah, there was only one section under 475.
Okay. Yeah, hold on, don't write to him. I think after this class, maybe let's think about it.
Okay.
Maybe it is 470, maybe?
There is a 470, and there's one section of that, but I thought that in the email he said it was supposed to be 475 Tech 3. But yeah, I could register for 470. I did, and then I dropped it because I didn't know if that was actually the right one or not.
Did it have a 706 on it?
I can check really quick. Um, 470, the section is, oh yeah, yep, it does have a 706.
I think that's what it is. Does it have my name on it?
No, it doesn't. It just says a TBA for instructor. And it went in as 1 credit though too. I'm not sure. Oh, I think I can change that also.
So let's do it after the class, okay?
Okay.
I do this all the time. Okay. So there was a homework due today. How was the homework? Was it pretty good? Okay. Hopefully that was give you a feel for what are the consequences of what we are doing today. We will actually talk about electromagnetic communication, basically a simple antenna, and that should clarify more. You have a home, I haven't posted this yet. I intend to post a homework 11, which will be due April 26th. It might be by end of today. I will actually make some questions for them. So, and there is expected to be one more homework, which I might make it optional. I haven't decided that yet, since there's less number of days there. And you have a final exam which is due May 3rd, Monday. That's on the first day of the exam week. Any questions in general? Okay, so so we started with electrostatics, then magnetostatics, and now we are doing electrodynamics in the sense that complete electric field can couple to the magnetic field, and we saw that this leads to what is called radiation. And I try to insist that the radiation, even though it seems like it's an approximation, it is pretty much like calculus, where even though the derivative uses the limit of r something going small, but it is exact in that limit. So similarly, radiation, we talk about situations where the distances are large, but when you really take that limit as r tends to infinity, it becomes exact in that sense. On the dome of a boundary, like if we are in a lab and you take r tends to infinity, then this is the only quantity that survives. Everything else is higher order, and anything 1 over r square in electric field will die off and really go to zero. But this quantity really contributes in there. And in that sense, it is exact if you keep all the terms. After that, we again tend to make approximations, and that's just a convenience. So what we have is radiation fields, let's say. We derived our electric field and magnetic field, and they look like this. So we usually start with the magnetic field, but we multiply it with the speed of light. That's just for dimensional reasons, so that that quantity on the left-hand side has the dimensions of electric field. Remember, velocity times magnetic field is in the Lorentz force equation. If you look at it, it's very clear that that has the dimensions of electric field. And its direction on the dome, like when I say the dome, that means r tends to infinity, right? Suppose you have a source at the origin and you want to talk about r tends to infinity, take a sphere of infinite radius, and that's what I mean by a dome around the origin. So r pretty much doesn't come into picture at all. All the r's has to cancel out. So in that sense, r hat crossed with a quantity which will decide what your magnetic field is, and that's given by mu naught over 4 pi. There's a 1 over r potential, so that's the radiation signature of radiation. Radiation fields are that electric and magnetic field go down as 1 over r, and it gets contributions from very close to the origin, and it's basically the time derivative of the current density that contributes. And current density, remember, is charge times velocity if it was a point charge, and derivative of velocity is acceleration. So if you ever have currents that are changing with time, that's one way of creating radiation. So, and the time is important. We will see how this contributes today. This plays an important part. This is plus r hat dotted with r prime over c. We will see, we won't neglect this term like we did in the point charge case, and we will see how this actually contributes. So that's your magnetic field. Once we have the magnetic field, electric field is pretty much got as, oh, there is a negative sign, by the way. So this has a negative sign in front. So let's see, the second time I'm forgetting, but yeah, so that's check that negative sign. And it is minus r hat crossed with C times magnetic field. What that means is if you have sources are confined to a region very close to the origin, so this could be a current loop, or today we will talk about currents, but this could be any kind of charge that is oscillating or accelerating in general, and you have R very far away, the limit R tends to infinity, so that's your dome. So on that dome, if I were to look for, so that's your R. If I look for the magnetic field, it is R crossed with, so there is some quantity in here that's a source. So this could be anywhere. It doesn't have to be in the Z direction. This is J's, right? Time derivative of J. All the collections give you a vector that, and R crossed with that, so that's your going into the page, right? So this is C times magnetic field. And again, you cross it with the electric field, and that's your magnetic, electric field. I think I said it wrong. Cross it with the magnetic field, and you get the electric field. And you do, oh, there's a mistake, right? Why is there a mistake? Let's see, R crossed with the magnetic field, R crossed with the magnet, and then you have to take a negative sign, so this should be the electric field. Why did I say there is a mistake? Because remember, E cross B in your electromagnetic wave always points in the direction of the propagation. So E cross B is the momentum. So E cross B should be in the direction of the momentum. And they each, all these three vectors will always be perpendicular. So that's a characteristic of electromagnetic wave, which is what we studied in introductory physics. There's one more feature you can write in here, even though we wrote magnetic field in terms of the source, it is also, because of the orthogonality, it is also equal to R cross E. So once you know one part of field, it is exactly the same on the other part. In fact, there is equal amount of energy in the magnetic field and the electric field, which you can show by taking the square of this square of the fields, and the momentum also can be calculated. Okay, so that's good. And this immediately tells us, or in fact, when Maxwell wrote his equations, very soon these equations were derived, and immediately it was realized that if we can have a charge density that's changing with time, how do you design this? You will make a current loop, right? You will keep a current loop in a room, in one corner of the room, and you will be able to get some electromagnetic wave on the other side of the room. And until 1870, this was never done. And the first time it was done was by hertz, the unit hertz that we use for frequency. So it's Heinrich Hertz who first time experimentally showed that that is possible. And these days we use it everywhere, our cell phones, our radio, our satellite communication, everything uses this. So let's do the simplest possible scenario. Let's have a current carrying wire. Let's oscillate the current, and let's see what kind of radiation we will observe around it, right? So that will be our exercise, and this we will call it a simple antenna, the simplest antenna in a sense. And I should point out that these days this has become very advanced. Like this is, you're going back in time, and you're really in the simplest possible geometry, but things have got very advanced, and but ideas remain pretty much the same. So what's the geometry one can think of? Let's have a straight wire, right? So we have a straight, simple wire. So it's one wire. Let's not worry about how it's ending and all that. And it is possible to have a current in this oscillate. Like think of an antenna. I think even these days you find these antennas where you have a simple rod, right? And that acts like an antenna often for television, if you don't have a cable connection, sometimes you have to use these antennas to emit and receive. You use it as a receiver when you're using it for your TV. But if you look at all this huge antennas that are, what do you call it? Yeah, radio or cell phone towers, right? How does a cell phone tower work, right? That's what we're talking about. There is special geometries being one uses, but we are just talking about just one simple wire, and we would like to observe it at a distance r. Very far away. That will be our dome in a sense. And let's have it along the z-axis. So that's our geometry. So this is your z-axis. Let's have the wire sitting on the z-axis, and the length of the wire, let's say, is, so this coordinate here is 0, 0, minus L over 2. And the top point there is 0, 0, L over 2. So that's the length of the wire is L, and it is exactly centered on the origin, and it is on the z-axis. This vector R can make an angle theta. It doesn't have to be on this plane. It can be any cone, right? So if you have a wire, you can have a cone around it. So that point R could be anywhere making an angle theta with respect to that. So that's our simple antenna, and we would like to know what's the magnetic field and electric field emitted by that. So let's write J for this, current density, right? And since it's a source, we will write this as R prime. Remember, this simple R is observation point that we have been always trying to use. So let's say this is T prime, and that's equal to, we will have the current in the direction of the wire, so it is Z hat. The current in the wire, let's say, is current I. If the current was a constant, nothing happens because we need a time derivative of the current, right? So let's have this facility that we will say this is a T prime dependent quantity, right? So it's a time dependent quantity, which we say is T prime. It's on the z-axis, so remember current density is current per unit area, so that's on the z-axis, so that's x prime equal to 0. Right? It is also y prime equal to 0. And it also, I have to specify that the length is L, right? So I have to specify that, so I have to multiply this further and say that this is a step function which survives only between minus L over 2 and plus L over 2. So this is a function which is 1 if this argument is satisfied. It is equal to 0 if the argument is not satisfied. We had used the step function before, so that's what we mean. So this angle theta should not be confused with this angle theta. It's the same letter, but we are recycling it in the same pretty much the same equation or same diagram, but hopefully contextually it should be straightforward. Okay. And we will get rid of that almost immediately. That's just a feature saying that it is right at that. Okay, so that's our current. So we immediately calculate time derivative of this. So let's do time derivative. So this is time derivative T prime of J or prime T prime. And of course, we have to evaluate this at T minus at the retarded time, but we will come back to that. First, let's just take the derivative. So you notice that the time derivative is only in the current. Notice how if you're designing this, it should be easy because you're just having a current carrying wire and you're passing a current which is time dependent. It could be an oscillatory time dependence, right? You just put an AC field, AC current in there. That's all one has to do. And this is Z hat. times di by dt prime. Since there is only one parameter, you can also say this is a total derivative, and sometimes you write a dot and that's, so this is del Ch of x prime, del Ch of y prime, and theta of minus L over 2 z prime to plus L over 2. Okay, that should be clear. We have to do this integral now. So remember, the integral of this quantity is what acts like the source. But before we do the integral, we had to evaluate this at a certain point. So let me write that down. So this is time derivative of t prime j. I have to evaluate this at t is equal to retarded time. At this point, let me just call that tr, but that means t minus r over c, that whole expression there. And that's equal to z hat times I dot, right? So instead of time derivative, let me say that's time I dot, right? That's a time, that means it's the time derivative. And I'd evaluate that at t minus r over c plus r hat dotted with r prime over c. But notice, what is r prime? Where is r prime sitting? R prime will be actually sitting on the wire, right? So r prime dotted with r hat will have this cosine theta in there. So let me clarify, let me do this first and then come back to that. So delta of x prime, delta of y prime, theta of minus L over 2 z prime plus L over 2. So R over C here is a observation point dependent quantity. It is x squared plus y squared plus z squared. No x primes in that. But when it comes to r prime dotted with r hat dotted with r prime, all my prime quantities, because of this delta function, sits on the axis. So when I dot it with r hat, I have a cosine theta coming in. So this is equal to z prime. So let me say this is r hat dotted with x prime I hat plus y prime j hat plus z prime k hat. Or actually, I don't have to write it like this, right? That is, it's easier to see this just as a geometry. So it is the magnitude of r hat, which is 1, magnitude of r prime hat, which will be just z prime, because it is on the axis, and the angle between them, so that's cosine theta. Okay. Is that clear? Any confusions there? I wrote it differently there. Any questions on that? Okay. So now we have the expression, now we do the integral. And that will pretty much, once we do the integral, that gives us the expression for the magnetic field. So let's do the integral d cubed r prime of j r prime to time derivative and evaluated at t is equal to t of r. That's the same as dx prime, dy prime, and dz prime, all going from all space. You look for sources everywhere in space, and the time derivative we evaluated, this is z hat I dot, notice, don't forget the dot, there is a time derivative to be taken, and then evaluate it at T minus R over C plus Z prime over C cosine theta, and that is delta of X prime, delta of Y prime, and the step function going from minus L over 2 to plus L over 2. The X prime and Y prime integral is straightforward. That goes away immediately, and the Z hat can come out of the integral, and the dz prime, because of the step function, gets limited in its integral. It goes from minus L over 2 to plus L over 2. Everywhere else, it goes to 0. And that's pretty much what it is. So that's I dot. So T minus R over C plus Z prime over C times cosine theta. To proceed further, we should specify our current, right? So let's specify our current. Let's choose a very simple form for current. That's equal to, let's say, some amplitude for the current, I naught, and let's say sine omega naught t. That omega naught is the frequency with which you're oscillating the current. So that, for example, if you're using your AC supply in your house, then omega naught will be 60, right? Is it 60 or 50 here? I forgot. Like in different countries, you have different. Do we have 60 cycles per second, or is it 50 cycles per second?
I believe usually it's 60.
60, okay, yeah, 60, yeah. So that's sine omega naught t. So this will be omega naught. If you use your AC supply, it will be 60 cycles per second. Yeah, thank you. So derivative of that, I dot t prime is equal to, take a derivative of this, so that's omega naught I naught times cosine omega naught t. We will also sometimes, instead of talking in terms of frequency omega naught, we will also talk in terms of wavelength. So omega naught will also be is equal to 2 pi over lambda naught times c. So distance cancels out, and then you have a time, right? So we will associate a wavelength also associated. At least that conversion is always available for us. Okay, so what is this quantity equal to? That we have to do that integral, and once we know the integral, we immediately know the magnetic field. Right? So let's do that integral. So this is equal to z hat times minus L over 2 to plus L over 2 dz prime times omega naught I naught times cosine of omega naught times, we have to replace this time. Oh, this is t prime. I had evaluated, replace all this t prime with this whole retarded time. So this is t minus r over c plus z prime over c cosine theta. That's it, right? If we can do this integral, which is straightforward because it's a cosine function, but notice there is a cosine inside a cosine, but not really, because we are integrating with z prime, so it is really linear in that. Cosine theta is just acting as a coefficient. It has some angular dependence, which will be interesting later on. But as of now, we can analytically get this done. So let's do this. So To do that, just expand out the cosine. Let's have the z prime separated out. So this is equal to z hat minus L over 2 to plus L over 2 dz prime. And let me write the omega naught I naught outside completely. Z hat. Is that within the region? Yes. And open this up. So this is cosine. So have this as one piece and that as a second piece. Right? Cosine of A plus B. So cosine of A plus B is cosine A cosine B minus sine A sine B. Right, that, let's write that as cosine omega naught T minus R over C times cosine of omega naught. Let's omega naught Z prime over C times cosine theta. And then there is another term which I will write as a separate integral. And this is Z prime, by the way. This integral is Z prime. And this is sine of omega naught T minus R over C times sine of omega naught Z prime over C cosine theta. Do you notice that even though it looks like a complicated integral, this is Z prime is the only term that's relevant. Rest everything is coefficients or constants, right? So that's just a sine integral. This whole thing comes out of the integral. That's a cosine integral. This whole thing comes out of the integral. This is going from minus L over 2 to plus L over 2. And the sine function is an odd function. So this does not contribute. So this integral does not contribute. So let's make that as a quiz. So in the quiz, so check out that this integral actually cancels out. Remember again that sine function can be brought out of the integral. So the z prime integral is straightforward, sine of z, except that coefficient will come in the denominator. So it will be a cosine function evaluated at the limits, and both should be the same limits with the negative sign coming in. So they should cancel. So prove that explicitly. And what's remaining is that cosine integral. So let's do that integral. Again, this function comes out, so I can keep that separately. It's z hat naught I naught cosine of omega naught T minus R over C. I will do this integral. Cosine integral is negative of cosine integral is, integral of cosine is sine. So it is sine of omega naught times z prime over C cosine theta divided by the coefficient in front. So that's omega naught over C times cosine theta. And you evaluate this at 2 points. Z prime is equal to plus L over 2 and Z prime is equal to minus L. That's your integral. When I evaluate it at minus L over 2, the sine function is negative, but I'm subtracting it. So basically the upper limit and the lower limit contribute exactly the same amount. The negative sign adds up. So this is equal to, and the omega naught cancels out. So this omega naught cancels out. So what we have is z hat times c times I naught times cosine function omega naught t minus r over c. And evaluate this at plus L over 2, and that is a factor of 2, right? So I put that factor of 2 also in front here, 2c I naught. And then I have sine of omega naught over 2. So it is L over c cosine theta divided by cosine theta. Okay. That's pretty much your source function. And from that point on, we can calculate the magnetic field and so on. We will do the explicit analysis of this next time. But for now, let me proceed and show what's the details that comes in here. So what we have at this point is, let me call this whole thing, yeah. So maybe alpha, right? Yeah. So alpha of, yeah, just let me not specify what it depends on. That's equal to d cube r prime d by dt prime shape t is equal to t of r, the retarded time. That we have calculated it to be exactly equal to z hat times 2 times c times I naught. There is an oscillatory term which is dependent only on t time and r over c, and there is another oscillatory term that depends on the geometry of the source, which is sine of, let me write that as, remember your omega naught over c is nothing but pi over lambda naught. So this is the same as pi over pi times L over lambda naught times cosine theta. What I did was omega naught over c is nothing but 2 pi over lambda naught, and the factor of 2 cancels out. That's cosine theta divided by cosine theta. And all these angles are important that will decide in what direction the intensity of this radiation will be. If you have an antenna at each angle, how much radiation will be there. Once we have this alpha, we have magnetic field given in terms of, yeah, I should say this is alpha, which is dependent on theta and phi. People R goes away. That's equal to minus r hat crossed with mu naught over 4 pi 1 over r and alpha. So that's alpha of theta and phi. It depends on the angular coordinates and of course on the geometry of the source also, or the properties of the source also. And electric field. Sometimes I also, oh, that should be a big vector, right? Sorry. This should be a vector. Alpha should be a vector. Sometimes I call it F, sometimes as a whole I call it K. Okay, so that's your problem. And we want to calculate how much is the power at the dome if you want, and that's given by power or the energy per unit time per unit angle. So this is your power. That's equal to r squared. That's the flux, if you want the surface area of the sphere at the very, even if it is very large, it is a very large r squared, but then in the denominator, if you have r squared, that will cancel out. So that's d omega, that's your solid angle at for any given angles phi and theta and phi. And its direction is r hat, that's your area associated with that particular solid angle. Dotted with E crossed with H. it is nothing but E crossed with B over mu naught. You're saying that's your solid angle. And so that's your vector hat. So that's your theta, that's your phi. We can replace this cross and dot. Our cross E is B, and we showed that this is nothing but, immediately this becomes R cross E is nothing but C times B. So we have R square the omega times C times B square over mu naught times C. Let's substitute this quantity in here for C times B, and we notice that this is equal to, in the book space, yes. So that's R square, the omega, C times B is nothing but this quantity in here, and the negative sign cancels out. So that's R hat crossed with mu naught over 4 pi times 1 over R. Alpha is nothing but it's in the Z direction, correct? So it's in the Z direction times alpha itself, right? So alpha theta phi. I took out the direction of Z explicitly. That's your squared quantity, and that is a mu naught times C. Again, remember, this is your Z hat direction, and that's your vector R. So angle between them is angle theta. So R crossed with Z will be equal to sine theta. There's two factors of R, so that cancels out. So we have d omega times sine square theta. Or let me first say this is sine theta. And then there is mu naught over 4 pi squared. And there is alpha theta phi squared. And that is 1 over mu naught squared times C squared. That is a factor of mu naught. Oh, did I miss something? Messed up, right? So this is mu naught and C. So there's only one mu naught and one C. Okay. So that's equal to the omega over 4 pi. Keep one of the 4 pi's with the d omega because that's going to give us a 4 pi and one more sine square, right? Lots of mistakes I made. I made some corrections here. This was sine square theta because R hat crossed with Z hat is sine theta. Square, that is sine square theta. Mu naught over 4 pi squared. 1 over R squared cancels out. And alpha squared, and there's a mu naught over C. One of the mu naught cancels out. And let me write this as mu naught C over 4 pi. And that's because I pull out one of the C's that's in the alpha quantity, and we have 2 times I naught. This is squared now, so this is cosine P minus R over C, whole squared, sine of pi L over whole squared. it seems like it's a straightforward expression, but let's check our dimensions first. So it's kind of a neat thing to see. And we'll come back and analyze this expression, but let me write this down first of all. So the power radiated, remember I can take r tends to infinity and still this contributes because there is no r dependence in here. Even at infinity, that will contribute at that angle. That's a whole point. And that's equal to, let me write this as d omega over 4 pi. And I want to talk about this in a minute. So what is this quantity equal to? And this is 4 I naught squared, and that is cosine square omega naught t minus r over c. That's sine square pi L over lambda naught cosine theta, and that is cosine square theta. Notice on the left side you have power, and on the right side, what are the quantities we have? We have cosine square, no dimensions, sine square, no dimensions, cosine square, no dimensions. So that whole quantity has no dimensions. Solid angle has no dimensions. So we are having a quantity like I current square times mu naught times C is equal to power. Right? So what do you think is the dimension of mu naught C? So if so P is equal to I square times, let's say, this quantity here. What is that quantity equal to from your electrical circuits? What is power in an electrical circuit?
That's the resistance, right? That's correct.
Resistance, correct, exactly. Like if you have a resistor, the power that you lose in a resistor is R. I square times R, right? That's the same as current times voltage. Current times resistance is voltage, so that's current times voltage. So it seems like mu naught times C over 4 pi acts like a resistance. And that resistance of what, right? That immediately raises the question, resistance of what? So let's calculate what is mu naught over C divided by 4 pi. That seems to have the units of resistance. So that's mu naught over 4 pi times C, which is 1 over epsilon naught times mu naught, which is the same as 1 over 4 pi times mu naught over C naught, epsilon naught. We have earlier talked about the product of the magnetic permeability and electric permittivity, but now this is a ratio of the two, and apparently that if you take the square root of that, that has the dimensions of resistance, and this is a property of vacuum. So are we suggesting that this is the resistance of vacuum? So whatever that is, that's a ratio. Let's calculate that. And for calculating, it's better to go back to this expression, right? So that's mu naught is 4 pi into 10 raised to minus 7 divided by 4 pi. C is, let's keep it exact. So this is 299, 792, 458. Right? That's like a telephone number. But that's exact. That's an integer, right? In the new SI system, that's exact. And this apparently has the units of ohms, right? In SI units, 4 pi cancels out. 10 raised to minus 7. 1, 2, 3, 5, 6, 7, right? So that's 29.9792.458 ohms. That's approximately 30 ohms. Right? that's what it is. It's interesting to see that that has this dimensions and that constant has this meaning. This plays an important role later in magnetic field. There is a unit of conductivity which always comes in terms of this constant, and that requires the Planck's constant also to show up. So there is a depth in there, but we will just point out that this is actually 30 ohms, and this constant is what shows up in our power. So what we have as of now is we have the power, and we have an explicit expression for it for a simple antenna. And next time we will come and see what actually that is, what can we do with this. What we will notice is that the time dependence is too fast in this case. It's oscillating 60 cycles per second, right? So for calculating the power, it is good to average it out. If you remember in any of the AC circuit, if you've handled any AC circuits, you basically average out things over the 60 cycles. So power, we will talk about average power, and we will be more interested in the angular dependence on that. So we will define those quantities, and very quickly we will get an expression, and then we will analyze in what direction of the simple antenna is the radiation a maximum, minimum, is there, like how would you send yours, how will you design your antenna, and how will you orient it so that you want to send signal to someone. And at this point, I'll stop and come back and work on that. Any questions, comments? Okay. Thank you. Yeah.
Thank you.
I think I got I think it's registered for now. I have it for 2 credits, and it is the 706 section. So yeah, I guess I referred to the wrong email. I thought it was supposed to be a 475 3. I didn't see the 706, so I think it's good now.
So 475 with 706 is available.
No, it's 470, and then it's 706. Yeah.
706. Just make a confirmation with Dr. Talapatra that this is indeed the case. Just have that number and confirm with him that I've registered. I hope this is the correct one. Like 706. Okay. He told me that it is 706.
Okay. Yeah, it should be 470 then. Yeah, it's probably just a different course